Section 2.6, mechanical vibrations. In this section, we are talking about applications of theory that we discussed. Consider the case where a small object of mass m is attached to an elastic spring of length L, which is suspended from a rigid horizontal support. Here is a picture. Now, an elastic spring has the property that if it is stretched or compressed a distance delta L, which is small compared to its natural length L, then it will exert a restoring force of magnitude K times delta L. Here's what we do next. We want to describe the motion of this object. In calculating the motion of the mass m, it will be convenient for us to measure distances from the equilibrium position of the mass rather than the horizontal support. Question is, what is the equilibrium position? The equilibrium position of the mass is that point where the mass will hang at rest if no external forces act upon it. In equilibrium, the weight mg of the mass is exactly balanced by the restoring force of the spring. Thus, we have the following formula: K delta L is equal to mg. Let y is equal to 0 denote this equilibrium position, and we take the downward direction as positive. We denote by y of t the position of the mass at time t. Question is how to find a formula for y of t and then how to analyze this formula. Here's a general approach. To find y of t, we must compute the total force acting on the mass m. This force is the sum of 4 separate forces: W, R, D, and F. W, which is equal to mg, is the weight of the mass pulling it downward. Number 2, the force R is the restoring force of the spring, and it is proportional to the elongation or compression, which is delta L plus y. One can show that no matter delta L plus y is positive or negative, R is equal to negative K times delta L plus y. Number 3, the force D is the damping or drag force, which the medium exerts on the mass m. Most media, such as oil or air, tend to resist the motion of an object through it. The formula for D is negative Cy prime. Lastly, the force F is the external force applied to the mass. Now let us put pieces together. By Newton's second law of motion, m times y prime prime is W plus R plus D plus F. Now let us replace this by the corresponding formulas. W according to what is written here, is equal to mg. We put here mg. R is this. We put here negative k times delta L plus y. We replace d by this, done, and we leave f without change. Here's what we do next. Let us simplify a little bit this formula. If we expand parentheses, we'll get the following. Negative k times delta L minus k times y. Negative k times y is over here. But what happened to mg and negative k delta L? Well, mg minus k times delta L is equal to 0. Here is y. It's written over here. mg is equal to k times delta L. So this minus this is 0. Therefore, the whole expression becomes this. Lastly, we move these two terms to the left. Here is our differential equation for y. Note that this is second order linear non-homogeneous differential equation with constant coefficients, and now we can use our previous theory to solve it. Any questions?
Yeah, what does K stand for?
K is some number, so it's written the restoring force of the spring is proportional to delta L plus y. So we put negative K because here we show that no matter this is greater than 0 or lesser than 0, R is negative K times delta L plus y.
Thank you.
All right, next. Before we discuss the general case, let us consider some particular cases of this equation. The simplest case is the following: free undamped motion. Free means f of t is equal to 0. Undamped means c is equal to 0. If this is equal to 0 and this is equal to 0, the whole thing becomes this. And now, if we divide both sides by m, m disappears from here. Done. 0 divided by m is 0. Done. And if we denote k divided by m by omega 0 square, we come up with this equation. This is homogeneous second order linear equation with constant coefficients. We perfectly know how to solve it. In order to solve it, we go back to section 2.2. This is case 3. So, step 1, write down the corresponding characteristic equation. Move this to the right. Done. Take square root of both sides. Know that negative omega 0 squared can be rewritten as negative 1 times omega squared. Root of the product is the product of roots. We replace square root of negative 1 by I. Square root kills square, or what is left is omega 0. And we can rewrite this as 0 plus minus omega times I. Now, if we compare this and this, clearly, in our case, alpha is equal to 0 and beta is equal to omega 0. Now we apply these two formulas, just a copy of these two formulas. We replace alpha by 0, beta by omega, and after all simplifications, here are two linearly independent particular solutions. Therefore, this is the general solution of our equation. By the way, instead of C1 and C2, we use letters A and B. Guys, any questions here?
The coefficient of C disappears, or because it's undamped, right?
Yes, it's written undamped.
Okay.
Here, C is from 3. Undamped means C is equal to 0.
All right. And why is the equation homogeneous again?
Yes, because it's written free. When we say free means there are no external forces. Capital F is equal to 0.
Thank you.
So free undamped. All right. Here is what we do next. This is the general solution of our equation. Question is, how to analyze this solution? For example, how to sketch the graph. In order to analyze this solution, let us rewrite the right-hand side in a convenient for us way. Please take a look at lemma 1. It turns out that this can be rewritten as this, where r is square root of a square plus b square. Delta is equal to arctangent of b divided by a. Here's why. Let us start from the right-hand side. It's over here. Let us go back to one of my pre-calculus handouts. So we click on pre-calculus, and then we click on section 7.2. Please take a look at this formula. Cosine of s minus t is cosine times cosine plus sine times sine. In our case, s is this, t is this. We apply the formula, the result follows. Here's what we do next. Take a look at this picture. According to this picture, if this is A and this is B, by Pythagorean theorem, this side is square root of A square plus B square. By definition of cosine, A divided by R is cosine of delta. Therefore, R times cosine is A. Similarly, by definition of sine, B divided by R is sine of delta. Therefore, R times sine is B. And now, let us replace R cosine by A, done. And let us replace R sine by B, done. Note that what is written here is exactly this. Therefore, indeed, y of t can be written as this. Folks, any questions here?
This is just a way to simplify, right?
Yes, this is a more convenient way to think about y of t. Y of t is equal to this, and this is identically equal to this. Here's what we do next. Question is, what is the graph of this function? Well, let us go back to pre-calculus again. Take a look at section 5.3, Trigonometric Graphs. We scroll down. Over here, the sine and cosine curves, this and this, have amplitude, absolute value of A, period, 2 pi over k and phase shift b. So period is 2 pi divided by the coefficient in front of x. Note that in our case, the coefficient in front of t is omega 0. Therefore, the period of this function is 2 pi divided by omega 0. Also, since maximum value of cosine is 1 and minimum value of cosine is negative 1, y of t always lies between negative r and r. So we come up with the following graph. This is r, this is negative r, period is 2 pi over omega 0. Here is our graph. R is called the amplitude of the motion, delta the phase angle of the motion, t0 period, omega 0 the natural frequency of the system. Next case, damped free vibrations. If you compare this and what we just discussed, the right hand side is still 0. But we do have the middle term, this term. So we are talking about homogeneous second order linear differential equation with constant coefficients. How we solve it? Again, we go back to section 2.2. Step 1, write down the corresponding characteristic equation. Done. We use the quadratic formula to find both roots. And now we distinguish 3 cases. Case 1, the discriminant. Discriminant is the expression inside square root, c squared minus 4km. Discriminant is positive. Case 2, discriminant is 0. Case 3, discriminant is negative. If discriminant is positive, square root is a real number, therefore both R1 and R2 are real numbers. Moreover, since the discriminant is positive, square root of discriminant is strictly positive number, therefore this is different from this. So roots are distinct. Basically, since R1 and R2 are real and distinct, we can immediately apply this formula. However, for future reference, we also mention that both roots are negative. Here is why. 4km is a positive number. Therefore, when we subtract it from c squared, the resulting number is strictly lesser than c squared. Therefore, square root of the discriminant is strictly lesser than c, means if we add or subtract from negative c a number which is strictly lesser than c, the resulting number is negative, which means both R1 and R2 are negative numbers. Anyways, this is case 1. Here is a formula for the general solution. We apply this formula, the result follows. Case 2. Discriminant is 0. We copy these formulas over here. We replace this expression by 0. This portion disappears. So R1 is equal to R2 is equal to negative c over 2m. This is case 2. roots are real and equal. According to this, y of x is c1 e to rx plus c2x e to rx. It's exactly what we do here. Instead of c1 and c2, we use a and b, and then e to rt, here e to rt times t. We factor out the common term. This is formula number 2. Lastly, discriminant is negative. Here's what we do in this case. Here is the quadratic formula. First, let us rewrite this. Let us switch positions as 4km minus c squared, the whole thing, times -1. Note that since this is negative, this is positive. A root of the product is the product of roots. Square root of -1 is I. Since this is positive, square root of this number is a real number. We split this fraction into 2 pieces and denote this divided by 2m by mu. So, in case 3, r1 is equal to this plus mu I, r2 is equal to this minus mu I. Now, this is case 3. In our case, alpha is equal to this, and beta is equal to mu. We replace alpha and beta in this formula by this, and the result follows. All right, now let us analyze this solution. We apply lemma 1 again. By lemma 1, this can be rewritten as r times cosine. And now the graph of this function is over here, because the graph of r times e is this. The graph of negative r times this is over here. So the graph of function y of t oscillates between these two curves. Note that indeed when t goes to infinity, this portion goes to 0. And thanks to the cosine component, our curve goes from here to here. Questions?
Professor, so you did 3 different versions of the question, right?
Yes.
So
we start with a really simple version when this is equal to 0 and this is equal to 0. It's case A. Then in B, we replace this by 0, but the left-hand side remains unchanged. This is case B. We are about to discuss the general case C. This one.
Okay.
Did I answer the question?
Yes, thank you.
Okay, now the general case. Our function is equal to f0 cosine of omega t, which is an external force. What is written here is a non-homogeneous second-order linear differential equation with constant coefficients. If we apply method of judicious guessing from section 2.5, we will come up with the following formula for a particular solution, this formula. Now, let us simplify a little bit this formula. Again, by lemma 1, what is written here can be rewritten as cosine of omega t minus delta times r. remember what these are. It's square root of this squared, which is over here, plus this squared, which is over here. Next, observe that here and here we have same expression. Over here we have this expression to the power 1/2. Over here we have this expression to the power 1. After the cancellation, we get same expression in the denominator to the power 1/2. On the top, we multiply f0 times cosine done. So this is a particular solution of our equation. Therefore, the general solution of this equation is the sum of two pieces. General solution of the corresponding homogeneous plus particular solution of this equation means this. Now, note that when t goes to infinity, this goes to 0. Here is why. We can see it in case 3. If t goes to infinity, this goes to 0. This is bounded, so y of t goes to 0. Same thing happens in case 2. If t goes to infinity, this times this goes to 0. But now we have to apply L'Hopital's rule. We rewrite this as a plus bt divided by e to positive power. Take the derivative, and then we will see that a limit is equal to 0. And lastly, since R1 and R2 are negative, when t goes to infinity, this goes to 0 and this goes to 0. So it does not matter we have case 1, case 2, or case 3. When t goes to infinity, this portion goes to 0. Therefore, we can use a particular solution of our equation as a good approximation of any solution of this equation if t is big. It's written here. Thus, for large t, the equation y of t is equal to psi of t describes very accurately the position of the mass m, regardless of its initial position and velocity. Very last case. Let us consider the following. We now remove the damping from our system and assume that f of t is equal to f0 cosine of omega t. Let us consider this. There are two cases. Before we discuss these cases, note that what is written here is a particular case of this, when c is equal to 0. Therefore, a particular solution of this immediately follows from this general formula if c is equal to 0. By the way, note that when c is equal to 0, tangent of delta is equal to 0, therefore delta is equal to 0. Means, in order to come up with a particular solution of this, in this formula, we replace c by 0 and delta by 0. Omega t minus 0 is omega t. This term disappears. Done. And now square root of the whole thing gives us m times omega 0 square minus omega square. Therefore, the general solution of this equation is equal to the sum of two pieces. General solution of the corresponding homogeneous equation plus particular solution of this equation. Case B. Suppose omega is equal to omega 0. In this case, we replace omega here by omega 0. Now, in order to find a particular solution of this, we use section 2.5, part 3. In part 3, we replace cosine by e to the power I times this. Done. Then, if we write down the corresponding characteristic polynomial, this characteristic polynomial is r square plus omega 0 square is equal to 0. Note that I omega 0 is a root of this polynomial. Therefore, it's case 2. A particular solution of this is the general polynomial of degree 0, a, times e, we copy e without change, times t, because once again, it's case 2. This is a root of the corresponding characteristic polynomial. This is the general form of a particular solution of our equation. Now we find constant a. In order to find constant a, we find first derivative, we apply product rule, we find second derivative, and then we replace this by this and y by this. It's done over here. After all simplifications, the left-hand side becomes this, but the left-hand side is equal to the right-hand side. It's over here. We cancel out e. We divide both sides by 2i omega, done. And then we simplify a little bit. We multiply top and bottom by I square is -1, which gives us this result. Lastly, we replace a by this. We apply Euler's formula to jump from here to here and expand parentheses. Since on the right-hand side we have cosine, a particular solution of this is the real part of this expression, means this. Done. Very last thing, the general solution of our equation is the sum of two pieces. General solution of the corresponding homogeneous plus particular solution of non-homogeneous. One can show that the graph of this function is over here. Folks, we are done for today. Any questions?
Professor, so there was a part that where you said y of t equals, or you could ignore psi because if you look at the limit, it goes to 0.
Yes.
But if the discriminant is distinct and real, won't the limit, it won't go to 0, right? Or
it will. Are you talking about this?
yes.
Once again, by L'Hopital's rule, the limit of this function is 0, because what is written here can be rewritten as this divided by e to positive power. And now if you take the derivative of the top is b, constant b. Derivative of the bottom will involve e to t again. And when t goes to infinity, b divided by infinity is 0.
Oh, sorry, I didn't see that you plugged in r. I understand.